Pleasure to see you. Our last speaker for the day is Hehe. Um, so while I assume she's with us and will appear on our monitor here soon. She's an assistant professor in the Department of Computer Science and the Center of Data Science at New York University. Yes. She has obtained her PhD in computer science at the University of Maryland, College Park. Before joining NYU, she spent a year at AWS AI and was a postdoc at Stanford University. And she's interested in building robust and trustworthy NLP systems in human-centered settings. Her recent research focus includes robust language understanding, collaborative text generation, and understanding capabilities and issues of large language models. Are you?
Oh, can you hear me?
Excellent. Yes, we can hear you. We can see you. Can you hear us?
Yes, great.
Excellent. Did you hear me introducing you or not?
Yes.
Okay,
yeah,
good.
I
All right.
guess we
Okay.
can. Thanks for the introduction.
Excellent. No, then I was sure. Okay, then over to you.
All right. Thanks, Andreas, for the nice introduction, and thanks for inviting me. I'm really glad to share some of our recent actual results in the past 2 years, overcoming spurious correlations in NLP problems. So to motivate the problem a little bit, actually now you set up a really nice context for this OD generalization problems in NLP. So I suppose I don't have to try too hard to motivate the problem, but let's consider this two-way classification task. So suppose we're given this simple corpus and we're asked to build a classifier. Just based on these sentences, there are two equally good hypotheses. So first is to predict input that ends with this exclamation mark. And the second is to predict inputs that give the positive recommendation. And it's unclear whether this training data is asking us for classify the punctuation at the end or classify sentiment, because both will give us very high accuracy. However, these two hypotheses can have drastically different predictions on new examples, such as the example shown here. So in this case, if the hypothesis we choose does not align with the underlying task, the model would have unexpected performance on all the examples, and we might see large performance drop. And this problem of relying on simple heuristics that's unaligned with the intended task has also been observed on multiple NLP tasks in the past several years. For example, the lexical overlap bias on NLI and paraphrase identification, as well as gender bias on co-reference problems. So in these cases, the underlying problem is that there are some annotation biases or selection biases on training data, and the model just latches onto the simple heuristics and then fail out of distribution examples or more challenging or adversary examples. Apparently, this would cause problem when we deploy the model into the wild, as the user queries may look very different from our training data. So the ID assumption almost never holds in practice. So in this way, a nice paper by Ribeiro et al. On checklist debugging. So they showed that even the commercial, for example, sentiment classification services would fail on simple perturbations such as negating a sentence or replacing the entity. So we don't really want to say that once you change Chicago to Dallas, suddenly the sentence score drops from positive to neutral. Okay, so how do we fix this problem? Here's the simple NLI example. So this is illustrating the negation bias. The majority of our training data that contains a negation word also happens to have the contradiction label. So in this case, the standard cross-entropy loss does not really tell us that this negation word and contradiction correlation is not reliable, because it would give us very high accuracy on the training distribution. So somehow we need to tell the model that it should not rely on the single negation words to make predictions. So how do we build in this inductive bias? One simple idea here is that we'll just learn from examples where this example fails, such as the example shown here. And suppose we know that this negation word is the problem in our data set, we could then build a bias classifier, meaning a classifier that's using only the negation word to make predictions. And then this bias classifier would tell us on which examples the heuristic works really well and on which examples the heuristic fails. And then we could try to emphasize these more challenging examples during our learning process. Okay, and then we instantiate this idea through two steps. So first, we train this bias classifier that uses only the spurious features such as negation words, using the standard maximum likelihood estimation or minimizing the cross-entropy loss. Then in the second step, we freeze the bias classifier, and then we train a debias classifier to learn what, to fit the residuals or to learn what cannot be learned by this bias classifier. So this would correspond to a kind of ensemble of the bias classifier and the debias classifier. And then at inference time, we will throw away the bias classifier and only using the debias classifier for prediction. Okay, so to test this approach, we train on MLI, which we know has various data set biases, and then we choose to test the model on an OOD challenge data, in this case, the Hans data set. That is created to exploit the overlap bias in data. So they contain examples where the premise has the hypothesis has high overlap with the premise, but is not entailed by the premise. So in this case, we see that if we fine-tune a BERT model on MLI, it has very high accuracy on in-distribution test set or on MLI. However, the performance drops significantly when we test on these more challenging or atypical examples from the Hans dataset. Now, if we use the residual fitting approach, in distribution, we see that the performance roughly stays the same, whereas the OD data, we have a large improvement. So one thing I haven't really described is what spurious feature do we use to train the bias classifier, which is the first step in our algorithm. So here, we tried 3 different spurious features: the hypothesis in the example, bag of words, or the overlapped words between the premise and the hypothesis. And clearly, you can see that even though they don't make much difference on the in-distribution data, the overlapped words as spurious features works the best on out-of-distribution data. So this really highlights the fact that the key for this method to work well is to have precise knowledge of the spurious feature that causes distribution shift. Because in this case, the Hans dataset is created by intervening on the overlapped words. So if our bias classifier is designed to detect such heuristics, it would work better on this specific OD dataset. Okay, so if you know the spurious feature, we can sort of tell the model to not use these spurious features during training. But in general, we don't really know these spurious features. And it actually takes a lot of experts' efforts to discover this annotation bias or spurious features in different benchmarks. So the question here is there a more general way to improve robustness without explicit assumptions on what are the spurious features in the data set? So there is a paper by Kaushik et al. On counterfactual data augmentation. So we were really excited by this approach that is somewhat similar to the Dynabench idea introduced by Dow just now. So here their idea is that given an example from an existing benchmark that may contain spurious correlations, and then we're going to ask humans to perturb this example to flip the label. So in this case, we may change fascinating to expected and captivating to mind-numbing to flip the label from positive to negative. And then we do this for a bunch of examples in the original data set or to augment the original data set. So why is this helpful? The assumption is that these spans that are edited by humans are the core features that would generalize to out-of-distribution data, because if humans edit them, of course, they would cause the label to change. That's why they're kind of causal, which is supposed to work under many different environments. Okay, so we were really excited by it, and we wanted to incorporate this counterfactual augmentations into training to improve the robustness of the model. So the straightforward way to do this, that's also tried by the original CAT authors, is to just add this data into the training data directly and then train our model as before. And then we also tried regularization techniques because sometimes the CAT data is very small compared to the original data set. So we could try to regularize the model such that the predictions is always both correct or both incorrect on the CAT pairs. But we wasn't able to get a lot of improvement by using this data in the training process. And actually later, we also see some mixed results from others. For example, my colleague Sam Bowman at NYU find that adding this counterfactual augmented data into SNLI doesn't really improve performance on NLI, which is even not that far from the SNLI data. But at the same time, there are also positive evidence from Kashabi et al. Showing that if you do this, create these natural perturbations or basically counterfactual augmented data for question answering, under some conditions, you could improve OOD performance. So intuitively, the counterfactual augmentation idea makes a lot of sense. So if they reveal useful features, then why aren't these data helpful? So this is the question that we wanted to investigate in this project. Okay, so to understand what's going on here, let's consider this simple two-way data set. The book is good, the movie is boring. Now, if you train a naive-based model on this data set, this model would assign positive based to book and negative based to movie, which is clearly spurious correlations. We don't want the sentiment to depend on the object types. So now let's say we augment this simple data set. So we could change the first sentence, the book is not good, to flip it to negative and change boring to fascinating. Now, if you train a model on this augmented data set, what additional constraints does this new data set impose? So basically it says that the prediction should be invariant to the unintervened features. So for example, book and movie are not edited by humans, and now they occur in both negative and positive classes. So if we train an NLP-based model, their weight should be 0, which is what we want. However, the problem here is that there are many features you could have intervened to flip the labels. In this case, for the first example, it happens to be the case that we didn't intervene this feature good, which is a useful feature. So according to the invariant constraint, the model prediction should also be invariant to good, which makes its weight to be 0, that is undesirable. The general problem here is that these perturbations or edits may not always cover all the features that could have intervened to flip the label. And the result is that it may limit what type of feature the model can learn. So to test this hypothesis in the real CAT dataset, so we train models, CAT pairs provided by Kaushik et al. That's created by crowdsourcing from the original SNI dataset. And then we test the OD test we use is MLI. So we want to transfer from SNI to MLI. And remember that the hypothesis we had is if we didn't intervene enough features, that would limit what the model can learn. So we try to, here on the x-axis, we try to fix the total number of training examples, and we change the number of edit types. So here we group all the edits by types, like inserting a word, deleting a word, or replacing a word. So, and then we increase the number of edit types while controlling the data size. So here the assumption is that if there are more edit types, then it would induce more different features. Okay, so clearly here we can see that as the number of edit types increases, the OD accuracy increases consistently. And this is the baseline if you just train on the standard SI dataset. So this suggests that even if we fix the dataset size, diverse edits would still lead to better OOD performance. So natural next question is, then would more CAD data naturally give us more diverse interventions and thus better OOD performance? So I want to look at the learning curve of using counterfactually augmented data. So in this case, we compare of training from CAD pairs versus the SNI data. And again, we compare the OOD accuracy on MLI. So in this figure, we can see that if we train on the CAD data, it kind of plateaus quickly, but it's very effective in the low data regime. So the blue curve is the performance. Sorry. The blue curve is the performance when we train on SNI, and the red curve is when we train on CAD. And so in the low data regime, CAD is really effective because even with a few examples, it tells you which features are useful based on this pair comparison. However, it plateaus very quickly, which suggests that even if we collect more and more CAD data, if we don't use any smart way to crowdsource this data, it might still limit the diversity of the edits, which makes the performance becomes not competitive with SNI. Okay, so the last question we checked CAD is whether these counterfactually augmented data actually reduce dataset bias, because this is one of the original motivation, right? If you intervene on the core features, it would reduce the correlation between the spurious feature and the label. So here we look at the label distribution condition on the fact that there is a negation word in the hypothesis. So in the original data or the seed data, we know that the label is more likely to be a contradiction because of annotation bias. However, we see that this is also true in the counterfactually augmented data, and it might even be amplified a little bit. And we saw the same trend when we look at examples with high word overlap. So in both the original dataset and the counterfactually augmented dataset, there are more entailment examples suggesting a spurious correlation between word overlap and entailment. So the lesson here is that intervention without control may not really fix the spurious correlation problems. If we just ask people to intervene on whatever feature they want to flip the label without controlling what type of feature they should intervene, this may not fix the spurious correlation in the dataset because they might intervene other features. Okay, so a quick summary. So here, so we got really excited by this counterfactual data augmentation idea because it's a promising way to improve robustness without having to explicitly specify the spurious features. However, through our analysis, it turns out we still need a better understanding of these spurious features. So if we think again about the assumption in CAD, which is that if the span is edited or perturbed to change the label, then these are the core features. Then we would soon realize that for many natural language tasks, typically there are so many things you can edit to change the label. For example, in this NLI example, you can literally change every single word in the hypothesis to change the label. So then does this mean that every single word in this hypothesis is a core feature? At the same time, there are other papers that argue that every individual word that's correlated with label should be spurious. So then it's kind of unclear what kind of assumptions should we make about the spurious correlations in language. And this motivates our next investigation, which is to try to have a better understanding of what kind of features are spurious in NLP tasks. So let's first consider the simple case here. So here, the spurious feature and the core features are disentangled, meaning that if we change the spurious feature, it doesn't affect the core features. And also the spurious feature is irrelevant to prediction, meaning that it doesn't affect the label. For example, in sentiment classification, the name of the director is a is such a spurious feature. If you change it, it doesn't change the label, or in object recognition, the background can be removed or replaced, and it wouldn't affect the label. However, the more complex case is that the spurious feature is often part of the core features. So they're necessary for prediction, even though they're not sufficient to cause the prediction alone. One example in NLP is the negation word in natural language inference. So obviously, we cannot throw away this negation word because the relationship to sentences are undetermined. So we have to use this feature for prediction. And similarly, image recognition, one example is the stripes on zebras. You cannot remove that. That's very, part of the reason why it's a zebra. But the reason we often consider these features to be spurious is that they're not sufficient for prediction. I mean that if we only rely on the negation word or rely on the stripes, it's not sufficient to cause the original label. Okay, so to formalize things a little bit, so here in the we consider a simple text classification example. So here's our input sentence. We assume that it is generated by some generator, say the reviewer writer, and Y is the label sentiment that is caused by these input words. So in this case, Titanic is a spurious feature, and it has no causal relation with the label Y. They may be correlated in our data set because they could be spuriously correlated through the pass through the generator. For example, the reviewers just tend to write good reviews for famous movies. So we would see this correlation in our data set, even though there's no causal relation between the movie title and the label. So this is one way to formalize these irrelevant spurious features, where there's no causal relation between the word and the label. For the more complex case, like the negation word, so here there is indeed a causal relation between the word and the label. However, the label also depends on many other features. So if we see this negation word alone, it's not sufficient to cause this label. So in this case, we say that the spurious feature is necessary for predicting the label. All right, so using this formulation or in this perspective of the necessity and sufficiency of features for prediction, we can say that a feature is spurious if it is not sufficient for predicting a specific label. However, this feature may still be necessary for prediction. So this then gives us two types of spurious features, the irrelevant spurious features and the necessary spurious features. So why do I care about this difference? Because these different types of spuriousness in the data prescribes different learning objectives, perhaps. So for the irrelevant features, we want the model to be invariant, meaning that if we change or remove this movie name, the prediction shouldn't change. Whereas for the necessary spurious features, the model prediction should be sensitive to them. This negation word obviously has a strong effect on the sentiment here. And the reality is that most spurious features in NLP we consider actually falls into this necessary spurious features. And these features turn out to be necessary to deal with than the irrelevant features. So in the next few slides, I will talk about some lessons we learned where we're trying to deal with this necessary spurious features in NLP. Okay, so the first question we investigate is whether the model generalized well if the spurious features is independent of the label on the training set. So this is actually many robust learning algorithm is trying to do. For example, we could subsample the data such that the label is balanced, condition on spurious feature. This is just enforcing the independence. So in this case, how well do these approaches work, necessary spurious features? So to test that, here's our experiment setup. So again, we use NLI as our test bed. So we train on NLI by fine-tuning Roberta large. And here specifically, we want to consider the two different types of spurious features. The irrelevant spurious feature, so here we use punctuation. So this is a synthesis-synthesized data set. So we add these punctuations to the end of neutral examples to inject the spurious correlation between punctuation and neutral. And then the other is the data set bias that's already in NI, which is a overlap bias. So the lexical overlap is spuriously correlated with entailment, but in this case, clearly, lexical overlap is a necessary feature for predictions. If you change or reduce the words that overlap, it's more likely to make the label non-entailment. So it definitely has the effect on the label here. So then during training, we subsample MLI such that the spurious feature is independent of the label. So essentially, we make sure that given the high overlap examples, the label distribution is uniform on those examples. And we test on the OD distribution. In this case, they're examples without the spurious feature or the low overlap examples. So the hypothesis here is that if we train on these examples where the spurious feature is independent of the label, and then when we test on OD data, we shouldn't see performance drop because the performance shouldn't be sensitive to the change of the spurious feature. Okay, so to remind you about the setting here, we're training on high overlap examples or examples with punctuation for the irrelevant spurious feature, and there's no correlation between spurious feature and the label. And then we do either in-distribution test or OOD test. Okay, so the blue bar is showing the in-distribution performance for different labels. And the orange bar is OD performance. So when we say that for punctuation, this is the irrelevant spurious feature, the OD performance is roughly the same with the in-distribution performance across different labels. However, for the necessary spurious features, the lexical overlap in this case, there is a large drop when we test on OOD data. And specifically, it seems that the model is still latching on to the overlap bias because when we test on low overlap and entailment examples, the drop is particularly large compared to the other two classes. Okay, so why do you still see such results even though there's no correlation between the spurious feature and the label during training? So if you look at this simple causal model, it becomes more clear. So for the irrelevant spurious feature, the core features in this case is grades that affect the label is not dependent on the spurious feature. So once we break this correlation, the model will just learn the core features, which works regardless of whether the example is Titanic or not. However, if you look at the other case, the core features depends on the spurious features. So now, even if there's no additional spurious correlation, this core feature will change, depends on whether the spurious feature changes or not. Which means that if we train on high overlap examples and test on low overlap examples, the model may encounter new features that cause the performance drop. Okay, secondly, we investigated another family of approaches which try to debias the embedding in a post hoc fashion. So once we train a model on potentially biased data set, the representation may encode the spurious features. We could use adversarial methods to remove the spurious feature from the representation. So again, we want to see if this approach will have different effect on irrelevant spurious features versus necessary spurious features. So here is the setup. So we're training on subsampled MLI, so the label is balanced condition on the spurious feature. And then we test the minority group, which is high overlap, non-entailment examples. And for debiasing process, we use this iterative projection method that's try to project out the spurious feature iteratively. And then we monitor two things. So one is the probing accuracy, which indicates whether the feature is removed from the representation. And the other is the task accuracy. So whether the devised representation is useful for prediction on this OOD test set. Okay, so in this figure, the x-axis is the iterations of this projection process. And the dashed line shows the probing accuracy. So we can see that for both the punctuation spurious feature, which is the red curve, and the overlap spurious feature, which is the blue curve, the accuracy drops gradually. The probing accuracy drops gradually, meaning that the removal is successful. However, if you look at the task accuracy, we see that for this irrelevant spurious features, removing that doesn't really have an effect on the task accuracy. But for the necessary spurious feature, if you try to remove it, the task accuracy would drop significantly. So meaning that even these minority groups, these spurious features are necessary to be in the representation, and forcing their removal would incur large performance drop. Okay, so the last point that I want to mention is that the necessary spurious feature also makes the evaluation quite tricky. So how do we evaluate model robustness to necessary features? For irrelevant spurious features, this is simple because we can just perturb the feature or remove it and see if the prediction changes or not. But for necessary features, if it changes, the label is likely to change. So really what we want to test is whether the model is relying on the spurious feature alone and ignoring the context. So typically in this case, we would construct OD examples that contain the spurious feature, but is matched with different labels. For example, entailed and non-entailed examples with high overlaps. So this is basically the examples constructed in Hans. But then there are many different ways that you could construct these examples. So in Hans, these examples are handcrafted. You could also imagine to sample this high overlap entailed or non-entailed examples directly from MLI. So we call this MLI subsets here. So now we have two ways to construct these OD data sets. And we could test the model performance on both sets. So here we train a model on MLI and test them on both data sets. So we can see that here this number indicates the performance difference between the majority and minority examples. So here, this gap on the Hans dataset is much, much larger than this gap on MLI subsets. So if we're looking at these results on MLI, we might conclude that, okay, there's not much drop between the majority and minority examples. The model is robust, whereas if we're looking at results on Hans, we would arrive at a different conclusion. So there is divergent results depending on which challenge sets we use. So the reason that it is happening is because when we're constructing this challenge sets, the high-level approach is that we want to fix the spurious feature and then change the context to see that if the model is considering the spurious feature together with the context, right? And then when we're changing the context, we're often likely to introduce new features. So in this Hans example, so the word overlap is fixed, but in order to solve this problem, the model will have to learn the specific syntactic structure, which may be unseen or very rare in MLI data. So here we're really conflict performance drop due to latching onto spurious feature versus failing to use these new features that's introduced in this challenge set. So in this case, maybe the model is not really using word overlap, it just doesn't know this specific syntactic construction. Okay, so to summarize, in the nice setting here is we know the spurious feature in the data set, and it is also irrelevant prediction. So we have a very clean setup. In this case, our main approach to fix the problem is to break the correlation. You could subsample the data to make sure the label distribution is balanced, conditional spurious feature. You could reweight the example. You could do invariance regularization, etc. So there's a lot of things we can do in this scenario. However, in the real setting, we often do not know, well, what is the spurious feature? And there are many spurious features, and we cannot hope to figure out all of them one by one. And often those spurious features are necessary for prediction. So in this case, just breaking the correlation is not enough. So in this case, it's a more important thing is to learn these patterns on the long tail, which might be fixed by improving the data diversity or use better representational learning. So this analysis also suggests that for this more complex setting, pre-training and scaling would be really helpful here if we want to cover the long tail. So in the rest of this talk, I would focus on some of the results we got with pre-trained models or these large language models. Okay, so after our first project, spurious correlation, and then this BERT came out, and also the other Roberta and the other large language models. So we were interested to see how these models perform in terms of robustness, even without all these robust learning algorithms. So here we, again, test and analyze. The in-distribution data is NI, out-of-distribution is Hans, and this is a family of pre-trained models. So ECM is a non-pre-trained model in this case. And we know that pre-training definitely improves in-distribution performance, but here we also see that the out-of-distribution performance improves as well. And we see a similar trend on paraphrase identification, where the in-distribution data is QQP, and we test on this pause data set that also try to exploit overlap bias in QQP.
Sorry, can you hear me?
Yeah.
Sorry, I tried to reach you to contact you before you started talking about this paper. I was but we have until 4 minutes really, and then actually we're getting kicked out of the room. So I was wondering if.
Oh, I see.
Yeah,
okay.
that's what, so sorry. I mean, it's all very, but we have to empty the room because it's actually
Sure.
cinema, and they will have a movie starting. So
no problem.
Maybe the people. So yes. For this reason, I'd like to, if that's okay with you, I would like to see if there's any question from the in-person audience.
Okay.
Or if I don't know if you want to make some final remarks, maybe.
Maybe I can wrap up.
Yeah,
quickly.
that would be great. Thank you.
So in I guess 2 minutes. Sure. Okay. So I guess I'll skip the details, but the conclusion from this result is that pre-training helps out of distribution generalization without any fancy learning algorithm. And in this study, what we find is that the key thing is that they can generalize very well from the minority examples in the data set. If you remove these minority examples, the pre-trained model also does not generalize. However, I think if I just have 1 minute, maybe I should show the Greg's meme. So recently, in the past several months, we really see this super exciting results from all these large language models, which raises a lot of questions for robustness research as well, which is, in this case, we're not even using supervised learning. So even if the training data has biases, we're not using them. It wouldn't create any problems, right? And also, what does OOD mean when we're using these very large language models in a few shot context? And so we try to investigate that with GPT-3. What we see is that GPT-3 is quite robust. So it would still suffer from extreme spurious correlation in the prompt, but it can be alleviated with verbalized labels, meaning that if you give it positive and negative to indicate the task is sentiment classification, or if you increase the number of in-context examples, it will quickly increase the robustness of this large language models in the in-context learning setting. So to wrap up, what we learned in the past 2 years is that if you want to tackle all sorts of spurious features in NLP, this is a very hard battle. And it seems the easy way to success is that we just use large pre-trained models and scaling. They have consistently improved model robustness so far. But this also raises a lot of open questions. For example, whether there will be other OOD problems, such as when the model encounters rare events, or maybe there are human biases. And also, we don't really understand how these models work. And with that, I will conclude by thanking my collaborators and take any questions if we have time.
Right. Thank you. Okay. We have 5 minutes till we are supposed to vacate the room. Is there a question from the audience, a quick one? Okay. In that case, there are 2 questions on the chat. I'll pick one. How could we automatically identify the necessary versus irrelevant spurious correlations? That is generalized to other tasks, or it still requires domain knowledge to find spurious correlations?
Right. So for the necessary and sufficient features, we will have to do interventions. So one way to do this is we could ask people to for example, change the word overlap between 2 sentences and see how often it would lead to label change. And based on that, we could estimate the how necessary that feature is to the label. So then I guess the answer is no. We still need to know what is the feature we want to investigate, and then do a simple perturbation experiment to figure out whether it is necessary to prediction.
All right. Thanks again. Distinguished speaker
Thank you.
again. Yes.